Our talk has three parts. The first one is background or goals, and the second one is construction methods, and the last one is some applications. Let's go to the first part, background and goals. Before we want to introduce some notations. Our semisimple modular tensor category will simply be noted by this notation, and our non-semisimple modular tensor category will be denoted by this. Here, the vector K means that the category of finite dimensional vector spaces. Rib H means that finite dimensional representation category of a Hopfalgebras H. In this talk, we only handle finite dimensional Hopfalgebras, so we agree that the Hopfalgebras H always finite dimensional. DH means that the quantum double of a Hopfalgebras H. GH means that the set of group-like elements of a Hopfalgebras H. H star means the dual of a Hopfalgebras H. HR means that it is a quadriangular Hopfalgebras with a universal R matrix R. Zn is the cyclic group of order n. And the UQG means that small quantum groups at the root of unit. Here, G is semisimple Lie algebra over complex number. Next, we recall that our modular tensor category C is a braided finite tensor category with a ribbon structure such that it is non-degenerate. Here, the non-degenerate means that the middle center of C is trivial. Let's give some examples. If we consider the quantum double of finite group, then its representation category RPG is semisimple modular tensor category. Another non-semisimple cases are some representation category of small quantum group UQG. Here we ask that the order Q is other number such that it is equivalent to the Gaussian matrix C of G. Observe that the above categories are actually representation category of Hopfalgebras. For more general case, given a Hopfalgebras H, the rib H is modular tensor category is if and only if H is a ribbon factorizable Hopfalgebras. Here we recall the definition of ribbon factorizable Hopfalgebras. It is a finite dimensional quadriangular Hopfalgebras HR with a ribbon structure theta in H, such that HR is factorizable Hopfalgebras. Here, factorizable means that the rank of R2 R is dimensional H. Let's give some simple examples of ribbon factorizable Hopfalgebras. Considering the dual space of ZP and let R be any quadriangular structure on KZP, which is determined by any non-trivial bicharacter, then with a ribbon element theta equals to unit, it gives a ribbon factorizable Hopfalgebras. Another non-semisimple examples are small quantum group UQSL2 with arbitrary quadriangular structure such that the order Q is other number. And since the ribbon element in this case is unique, we omit it. Actually, these two Hopfalgebras not only give modular tensor category, but also their representation category are prime modular tensor category. So we need to recall the definition of prime modular tensor category as follows. A modular tensor category C is prime if every topological non-degenerate braided tensor subcategory is equivalent to either C or vector K. Actually, the semi-simple version of this definition is obtained, is defined by Beijing in 2003, but the non-semisimple version of this definition is defined by Language and Wharton in 2022. Let's give some remarks about this definition. Here, the topological subcategory D means that means that the object of D is closed for subquotient. That is to say, any object X in D, if we consider subobject of X or quotient or object of X, then it is also in objective of D. Since prime modular tensor category are actually building blocks of modular tensor category, we give some more examples in this place. Considering the rep D, the nth power 2, then it is prime modular tensor category. Another non-simple examples are some representation of small quantum group UQG such that the order Q is order number, and it is co-prime to the Gaussian matrix, a determination of Gaussian matrix of G. And here we ask that G is simply algebraic. Since we will discuss some decomposition about modular tensor category, we recall decomposition theorem as follows. Every empty modular tensor category is equivalent to a finite direct product of prime modular tensor categories. And the simple version is also obtained by Beijing, but the non-simple version is obtained. Any question? Is obtained by Language and Wharton in 2022. Let me give some examples for decomposition theorem. If P is other prime, then the rep D, the nth power P is direct product of C alpha and C R inverse. Here, alpha is any group isomorphism from the nth power of P to its dual group. And the detail of C alpha we don't list. Now we want to give some non-simple examples. Considering the quantum double of Hopf algebra of dimensional P4, then its representation category is direct product of rep P and rep UQSL2. Here we ask that the order of Q is P such that P is order prime. Since we mainly focus on constructing modular tensor category, so we will recall some related construction methods. This theorem is obtained by Beijing in 2003. Let D be a semi-simple MTC. Let E be a semi-simple tensor subcategory, and denote the relative microcenter of C by CDE. Then the microcenter of CDE just equals the microcenter of E. As a consequence, CDE is modular if and only if C is modular. Hence, there is a way to consider relative microcenter to construct some simple modular tensor category. But what about non-simple modular tensor categories? In 2019, Symmetry generalized the double centralized theorem to non-simple cases as follows: let D be a non-degenerate finite braided tensor category. Let E be a topologism braided tensor subcategory. And considering the relative megacenter of CDE, then the relative megacenter of CDE is just E itself. Using this result, Langwitz and Wharton generalize the Miller's result to non-simple cases. Let D be a modular tensor category, and let E be a topologism braided tensor subcategory, and denote the relative megacenter of C by CDE. Then the megacenter of CDE is just the megacenter of E. As a consequence, CDE is modular if and only if E is modular. The only generalization places are D not must be simple, and here the E is not here the D can be a topologism braided subtensor category. Let's talk about our goals of this talk. Since above methods and the representation of Hopfalgebras produce many modular tensor categories, so we focus on constructing ribbon factorizable Hopfalgebras to obtain more modular tensor category by using its representation category ribh. And specifically, our goal is divided in two parts. The first part, we want to obtain some methods of construction ribbon factorizable Hopfalgebras to cover some interesting ones, such as DG and UQG. The second part, we want to use our construction method to find more interesting prime modular tensor categories by using its representation category, ribh. With these goals in mind, let's go to our second part, construction of ribbon factorizable Hopfalgebras. To construct ribbon factorizable Hopfalgebras, we use two steps. The step one is to construct factorizable Hopfalgebras, and the step two is to find give ways to find ribbon elements for a given quasi-triangular Hopfalgebra. Now let's talk about the step one. Assume HR is a factorizable Hopfalgebras, and let BR be the bilinear function from H star tensor H star to K given by BRF tensor G equals to F tensor G R to 1 R, and let R and let phi R be the linear map from H star to H given by phi R F equals to F tensor identity R to 1 R. Then suppose K is a sub-Hopfalgebra in center of H. Then we have the following central extension of Hopfalgebras. Here, the L is quotient Hopfalgebra of pi induced by the sub-Hopfalgebra at K. The following result tells us when the Hopfalgebra L is a factorizable Hopfalgebra. Here, the L bar is a quasi-triangular structure on L induced by the projection pi. Let me show it. If the bilinear map BR restricted to phi R inverse k tensor phi R inverse k is non-degenerate, then the above L I bar is a factorizable Hopfalgebras. Let me give a remark. From this result, obviously it recovers the quantizable cases. And if we consider H equals to quantizable of positive part of UQG, and let P be the Hopfalgebras generated by the central group-like elements of H, then the L is just the small quantum group UQG. And if we ask that the order of Q is odd number, then this conditions hold. So the result actually recovers the classical case UQG. In fact, the above results is an application of relative microcenter as follows. Recall that we have recall the following relative microcenter. Let D be your non-degenerate finite Bragg tensor category, and let E be your topologism Bragg tensor subcategory, and denote the relative microcenter of E by CDE. Then the microcenter of CDE is just E, the microcenter of E itself. So CDE is non-degenerate if and only if E is non-degenerate. If we apply this theorem to our proposition, that is to say, if we let D equals to representation category of H, and if we let E equals to representation category of L, then this condition is exactly the condition that CDE is non-degenerate. So we get what we want. In our first test to construct ribborfactorizable Hopfalgebras, we think that the construction of factorizable Hopfalgebras is more difficult than obtain ribbon elements. But later we found that find the ribbon elements for a triangular Hopfalgebras is usually not that easy, because in most cases the Hopfalgebras H itself is very complex, such as some lifting of small quantum groups. So the ordinary method, the ordinary method to find ribbon elements requires that we should know the dual of Hopfalgebras H. That is to say, we should know some information about H star, but H star is usually some complicated. So to overcome this difficulty, we will introduce two ways to find the ribbon elements. Let's talk about the first way. Assume HR is a quasi-triangular Hopfalgebras satisfying the following three conditions. The first condition is the central group-like elements is just unit, and the second condition is the order of GH is 2n minus 1 for some n, and the second and the third the last condition is the square of n S such that its order is another number n, then the minus n power of GU is the unique ribbon element for HR, where G equals to U SU inverse, and the U is uniquely determined by the universal R matrix R. Here we omit it. Let me give some remarks about this result. if we consider small quantum group UQG such that the order of Q is odd number, then we can check that these three conditions hold very quickly. So this way recover the case of UQG, but unluckily the condition 2 here requires that the order of GH is odd number. But what about the case that the order of GH is even number? So we need the another way as follows. Assume HR is a quasi-triangular Hopf-algebra and H is generated by AI. I is greater than 1 less than n as an algebra. If the following two conditions hold, the first condition is the central group-like elements is just unit, and the second condition is the square of uncode AI equals to lambda AI for all I is greater than 1 and less than n, where lambda I is root of unit with order in K. Then there is a unique ribbon element for HR, like the third one. Observe that we don't ask any, we don't give any restrictions on the order of GH, so it can apply to the case the order of GH is given. Moreover, we can give the above unique ribbon element concretely, but we omit it in this place because it is slightly like the ribbon element given in third one. There are about two ways to find the ribbon elements is meaning to avoid discussing the dual Hopf-algebra of H. The main proof either of the above two ways is divided can be divided in two steps. The step one is we use one correspondence between ribbon elements and some special group-like elements, which we denoted by A, and the elements of A such these conditions. So we change to discuss this set A to obtain ribbon elements. This step 2 is to use the central group-like elements is trivial, and we can use two different fourth power of algebras formulas. Since the conditions gives an expression of fourth power of S, and the quasi-triangular Hopf-algebra itself gives a formula for fourth power of S, and so we will obtain what we want. If we combine the construction of factorizable Hopfalgebras and the ways to find ribbon elements, then we actually obtain two ways to construct ribbon factorizable Hopfalgebras. The following content, we will use these construction methods to construct modular tensor category concretely. Now, let's talk about our last part, the construction of non-semisimple modular tensor categories and construction of semisimple modular tensor categories. In this part, we mainly obtain two families of non-semisimple modular tensor categories, which we denoted by rib H omega n, rib K alpha n. In the following, we will see that the Hopfalgebras H omega n and K alpha n are actually some generalized small quantum groups. And we further show that these two categories are not tensor equivalent to any representation category of small quantum groups. Then we use the construction method to construct a family of semi-simple modular tensor categories, which we denote ribborfactorizable. Here, APQ is a family of semi-simple Hopfalgebras. Although it is not prime modular tensor category, we do prime comparison for it, and we compare APQ with some semi-simple ribbon Hopfalgebras for in some degree. Before this, we wanted to talk more about representation category of small quantum group. As we know, some representation category of small quantum group actually give prime modular tensor categories. So we have enough reason to believe that some representation category of generalized small quantum groups can also give prime modular tensor categories. And the following, we will give a positive answer to this idea. Now, let's recall the definition of the Hopfalgebras of UD reduced, which was introduced by Andruszkiewicz and Redford and Schneider in 2010. Let theta be a natural number and G is an abelian group, or reduced YD data. D reduced is a triple, which is FIGI chi I, where FIGI belongs to G, chi I belongs to the dual group G, such that chi J Gi equals to chi I Fj, FIGI not equals to 1. Usually, we will call the matrix chi J Gi by the breeding matrix of the Hopfalgebras UD, and the Hopfalgebras UD is determined by the data D and the abelian group G. Here, we don't list its generator and relationships since it was a bit complicated. But we can talk more about the Hopfalgebras UD reduced as follows. For example, given our simple algebra G, if we denote its Gaussian matrix by C, let R be the rank of C, and let N be the order of Q. If we let G equals to the R copies of the N, and Fig equals to Gi, which are generators of G, chi I Fj equals to Q di Aij. Here, di Aij is the Gaussian matrix of C, and di is determined by the Gaussian matrix C itself, and the order Q. Then the Hopfalgebras UD reduced is just the small quantum group UQG. In this mean, we will call that the Hopfalgebras UD reduced is a more generalized small quantum group if it is finite dimensional. So similar to the representation of UQG, we want to know how to use representation category of UD reduced to obtain prime modular tensor categories, and we hope that we can obtain prime modular tensor categories from this way. with this demand with this other demand, we construct the following two families of generalized small quantum groups, which we call H omega n and K alpha n. Now let me give you the first family, H omega n. To define H omega n, we just define the data D reduced and the group G assume n is greater than 2 and n is covariant to 7. Let G equals to Z2n cross Z2n, which the generators are denoted by AB. Let G1 equals to A and G2 equals to B, and F and define F1, F2 properly by solving the above equations here. Here we ask that n is covariant to 7. To obtain to define K1, K2, we need n's or two n's primitive root of unit omega. Then we can define K1, K2 as by the following Brighting matrix, which the first row is -3 power of omega and omega. The second row is the square of omega and -3 power of omega. Then the Hopfalgebras UD reduced is denoted by H omega n by us. By computation, we know that its dimension is eighth power of 2n, and note that the grading matrix here is just Gaussian type A2. So we will show that the representation category H omega n is actually prime modular tensor category as follows. If n is covariant to 21, then H omega n is actually prime modular tensor category as what we want. Moreover, we show that it's not tensor equivalent to any representation category of UQG. Here, we just list some of the algebra since we have shown that H omega is prime modular tensor category. The proof adders is divided in 3 parts. The first part is to show H omega is modular tensor category. In this place, we use the construction method of ribborfactorizable Hopfalgebras, and note that the group-like element of G of H omega n is even order. So we need to use the V2 to find the rib elements. And the second part is to show that H omega n is prime. To do this, we show that there is a low non-trivial quotient of H omega n. That is to say, the only quotient of algebra of H omega n is just basic field. Is just the field K itself or H omega n. And the last part is to show the rib H omega n is not tensor equivalent to rib UQG. To do this, we just use the dimensions and compare their one-dimensional representations. Similar to above family of ribborfactorizable Hopfalgebras H omega n, we will construct another family of ribborfactorizable Hopfalgebras K alpha n. The reason for this is that we guess that not only the Gaussian matrix, the Gaussian type Brighting matrix give prime modular tensor category, but also the non-Gaussian type variety matrix can also give prime modular tensor categories, and we will give a positive answer. Let n be an odd number, and define G and D reduced as follows. G equals to Z3n plus Z3n, and its generators are A and B. Then G1 equals to F1 to A, G2 equals to F2 to B, and let alpha be 3n's power of primitive root of unit. Define chi1, chi2 by the following variety matrix. The first row is minus 2's power of alpha and alpha. The second row is alpha and s power of alpha. Then the Hopfalgebras determine UD reduced given by the above data G, and D reduced is denoted by K alpha n. By computation, we also know we know that its dimension is 10 power of 3 and multiple 6 power of n. Observe that the variety matrix is not Gaussian type, and recall that we hope to construct prime modular tensor category by some non-Gaussian type variety matrix, and the following result actually give the positive answer as follow. If n is equivalent to 3 and n is other number, then P alpha n is actually prime modular tensor category, and we show that it's not tensor equivalent to RIP for any simple Lie algebra G. Here we also only list simple Lie algebra G. The proof ideas of this theorem is similar to the proof of theorems above theorem. The only difference is we use the first way to find the ribbon elements for this triangular Hopfalgebras K alpha n r. By considering dimensions and the ribbon elements, we also know that H omega n K alpha n are not the ones given by language and Wharton in 2022. Next, we will use our construction methods to obtain some simple modular tensor categories. To do this, we give some observations as follows. Note that the small quantum group UQSR2 is quotient of quantum double of Taft algebra, and the Taft algebra H n square is self-dual. Here we ask that the order Q is n, is n, and n is other number. Based on this observation, we hope to find a non-trivial self-dual simple Hopfalgebras to start its quantum double, and then we use the quotient of quantum double of quotient of quantum double to give some simple ribborfactorizable Hopfalgebras. So we choose the Hopfalgebras A0, which is constructed by Jiraki. Another reason we choose the Hopfalgebras A0 is that its dimension is PQ square. We know that the dimension if we know that or simple Hopfalgebras with prime dimension or PQ dimension or P squared dimension are all trivial. So we can read that the Hopfalgebras A0 here is a simple non-trivial self-dual simple Hopfalgebras in some degree.
Using above construction methods, we show that if we choose some special central group-like elements in quantum double of A is 0, then we do the quotient, and we will obtain ribborfactorizable Hopfalgebras. Here we denoted it by APQ, and the APQ has dimension P4 and 3 power of Q. So we want to ask, does RIP APQ or prime modular tensor category? Unluckily, it is not prime modular tensor category. To see this, we use generators and relationship of APQ as follows. The APQ is generated by x, y, z, i, e, g. Here, I is greater than 1, not less than q. G belongs to G as an algebra. Here, G is the non-commutative finite group, non-commutative group of order PQ. At first sight, these relationships are a little complicated, but note that the element x, the I, e.g. Are just like the group-like elements, or the dual of group-like, or the dual of a group algebra. So the only non-trivial element is y. For example, yx equals to xy t's power of y, and delta y equals to this. And we get the universal R matrix of APQ concretely by this. And and we will use this to deduce that the representation category of APQ is not prime modular tensor categories. The APQ is equals to the derivative product of ZQ and DGPQ. Here, GPQ is above non-commutative group with order PQ. The main proof errors are two parts. The first part is to use algebraic relations to show that the quantum double of DGPQ is actually a quotient Hopfalgebras. Moreover, from the R matrix given by this form, we know that the induced R matrix of DPQ is actually is actually a factorizable Hopfalgebras. So we can use the Lieber's result to obtain this result. The difficult part is to show the representation category of DGPQ is prime, and to do this, we use classification results about a simple Hopfalgebras of dimensional PQ square, and also we see that the RIP APQ is not prime modular tensor category, but we show that the Hopfalgebras APQ is not tensor product, is not isomorphic to tensor product of trivial Hopfalgebras and triple doubles. Here, trivial Hopfalgebras means that the group algebra all is due.还有事？没事，多说点。行，好，继续。Since the time permits, then we will talk more about theorem 5 and theorem 6. In theorem 5, we have shown that the main idea of its proof. To see it, to see more detail, we use above steps to show if the PQ is pre-modular tensor category. We use the first step is to show that all the non-group algebraic quotient are not factorizable. To do this step, we mainly use that there is no factorizable Hopf algebra or a semisimple factorizable Hopf algebra of dimensional PQ square. Here we ask that Q divides P minus 1 and and then the remaining piece are the group algebraic quotient. To do this, we compute all the group-like elements of the dual of DGPQ, and we find that its form is one tensor alpha. Alpha belongs to the dual group of GPQ. So from this form, we know that all the group algebraic quotient are actually not factorizable. So combine the step 1 with the step 2, we know that there is no quotient Hopf algebra of GPQ such that the induced R matrix gives factorizable Hopf algebras, and from the decomposition theorem of modular tensor categories, we will know that the RIP DGPQ is actually a pre-modular tensor category. About the theorem 6, we wanted to talk more. So actually, theorem 6 states that APQ is not isomorphic to any tensor product of trivial Hopf algebras and triple doubles. To show this, we mainly use the following two steps. The step 1 is to show that GH star, the intersection of GH star and ZH star, acts on GH, the intersection of GH and ZH is trivial. That is to say, any element alpha belongs to this set, and any element G belongs to this set. Then we have alpha G is unity. Then we use step 1 to show that APQ is actually not the form KG tensor K for any Hopf algebra K and any group G. So we can use the dimensional of APQ, which is P square and P square 3 power Q, to show that APQ is not trivial Hopf, is not tensor product of trivial Hopf algebra and triple doubles. Since there has many times, so we want to talk more about the above generalized small quantum groups, UD reduced, which when it is finite dimension, we want to talk how to apply our construction methods to UD reduced. Recall that let theta be a natural number and let G in an abelian group, fixed or reduced YD data D reduced FIGI, then we can define an object in that general model of PG as follows. Here, Y is the direct sum of PVI, where the basis VI belongs to VGI KI, which means the coaction, though VI is just GI tensor VI, and the action is determined by this character. And so we have then an positionalization as follows. Here, the BV is just the Nernst algebra of V in this related tensor category. Then the following result shows that the Hopfalgebras UD reduced is isomorphic to the quotient of quantum double dA as Hopfalgebras, where KIFI is a central group-like elements of dA. That is to say, we have the following central extensions. The Hopfalgebras K is just the Hopfalgebras generated by KIFI, and the Hopfalgebras H above is just GA, and the quotient Hopfalgebras is just the UD reduced. So we can use central extension method to obtain that the UD to obtain that when UD reduced is actually a factorizable Hopfalgebras. Moreover, we can apply our ways to find the ribbon elements for UD reduced. So this is our main ideas to discuss the Hopfalgebras UD reduced. I think all the above results obtained by us is referenced by the paper in Honf, which is constructing modular tensor categories with Hopfalgebras. I think I will stop here, and thanks for listening.
Any question? Any question from